Welcome to Circuit Masterclass, your go-to channel for everything in power systems, transmission, and distribution engineering. Don't forget to check out circuitmasterclass.com for in-depth blogs and bonus content. We have provided the website link below in the description. Let's get started. Normally, the manufacturer manufactures battery banks for 220 volt or 110 volt systems used in high voltage transmission substations. These batteries are of the C10 type, which means the battery can deliver its rated current continuously for 10 hours without dropping below its minimum specified voltage. Suppose there are 110 battery cells connected in series in a battery bank to produce a rated voltage of 220 volts DC. The normal voltage per cell should not drop below 1.85 volts after 10 hours of continuous operation. Although the standard allows this voltage to go down to 1.75 volts. In our case, we will consider it as 1.85 volts. Now, we consider the continuous load imposed on the battery bank when the charger is off, such as during a total blackout. Since the battery is of C10 type, it must supply the continuous load for 10 hours. Continuous load includes the relay load, which consumes DC power even when not operating. The substation automation system, SAS, various IEDs, and some indicating lamps also draw continuous power. Additionally, miscellaneous circuits such as the firefighting system and AC distribution board are connected to the DC system and consume continuous load. Next, we consider the emergency load, which refers to the emergency lighting load. In the event of a total blackout during nighttime, all emergency DC lights will turn on. We consider this extreme condition to calculate the maximum lighting load consumed during 10 hours for the emergency lighting purpose. Now we consider the momentary load. Initially, suppose the bus differential protection operates, causing all 220 kilovolt circuit breakers to trip simultaneously. Although this occurs within a few hundred milliseconds, we consider a duration of 0 to 1 minute. Here, we calculate the current drawn from the battery if all 220 kilovolt circuit breakers trip at the same time. Another momentary load occurs when, after a maximum blackout of, say, 10 hours, AC power needs to be re-established. Sequential operations must be considered. 1. Close 1, 2, 2. 0 kilovolt incoming feeder to energize the bus. The closing coil will consume DC power and the DC-operated motor will also draw power. 2. Close the 220 kilovolt transformer breaker, which consumes DC power for both closing and spring charging. Although the 220 kilovolt bus differential operated, the 33 kilovolt feeders were not tripped, but operators might have switched off all the 33 kilovolt feeders. This is to avoid any backfeeding to the 33 kilovolt system from any 33 kilovolt feeder. During this period, if any consumer starts a generator, that may backfeed the 33 kilovolt system. Therefore, generally, we switch off all 33 kilovolt feeders manually during a blackout. 3. Therefore, we have to close the 33 kilovolt circuit breaker connected to the transformer, which also consumes DC power for closing and spring charging. 4. Finally, switch on the 33 kilovolt breaker associated with the station transformer bay, which consumes DC power as well. All these operations are assumed to occur within the last 1 minute of the battery cycle to restore the AC power, and the corresponding peak load drawn from the battery must be calculated. The first row represents the 220 kilovolt feeder panel. It has relays, indication lamps, which will consume continuous loading. The manufacturer provides data for the wattage consumption of the panel under continuous operation. If we divide that wattage by 220 volts, we will get the current rating, ampere loading. There are 6 such panels. Therefore, the continuous loading of each panel will be 6.81 amperes. This continuous load will be considered under 3 columns: 0 to 1 minute, 1 to 599 minutes, and 599 to 600 minutes. The momentary load of the panel and its corresponding current can also be calculated by dividing the wattage by 220 volts. Since there are 6 such panels, the total value will be multiplied accordingly. However, we will consider the momentary load as 0 for 0 to 1 minute, 0 for 1 to 599 minutes, and 0 in the last column as well. This is because when a fault occurs in an individual circuit, only the relays associated with that panel will operate and absorb the power. For bus differential protection, when all circuits trip simultaneously due to a bus fault, the relay of the bus differential panel will operate and absorb the power, not the feeder panel relays. Now, coming to the transformer panel, the same logic will be applicable. The continuous DC load of the transformer panel is 3.7 amperes. The momentary load can also be calculated, but again, we will consider it as 0 in all 3 columns because a transformer does not trip individually. It only trips during bus differential protection. For the bus coupler panel, the same logic is applicable. Only the continuous load will be considered. Next, the bus bar protection panel, differential bus bar panel, is important. Its continuous load will be accounted for in all 3 columns. However, during a bus differential protection operation, when all circuit breakers, 6 feeder breakers, 3 transformers, and 1 bus coupler, in total, 10 breakers trip simultaneously, the momentary load will rise significantly. This results in a peak current in the 0 to 1 minute column, but 0 current in the other 2 columns. Now come to the 33 kilovolt panels. Let's consider 33 kilovolt feeder panels. The continuous load is this, and the related ampere loading is this for each panel, and there are 13 feeder panels. So the continuous load will be 13 multiplied by 0.476 ampere. That is 6.18 ampere. And as this is a continuous load, this will occupy this column, and that column. Similarly, we come to the 33 kilovolt transformer panel. The continuous load is this, and the continuous ampere rating is this for 3 such panels. The continuous ampere load will occupy these 3 columns. But here, you see, the momentary load we have written as 0 because during differential bus protection of the 220 kilovolt system, 33 kilovolt breakers will not trip. So for that event, the momentary load will be 0. The same thing we can say for the 33 kilovolt bus coupler panel here. There will be a continuous load, but there will be no momentary load for the same reason. And then we will consider the 33 kilovolt SST panel. And as per the same logic, there will be a continuous load, but no momentary load. Again, I am repeating. Because of differential bus protection operated, no 33 kilovolt feeders will trip. So no relays in the 33 kilovolt panel will actuate during differential bus protection of the 220 kilovolt system. But the total blackout only occurs by differential bus protection trip of the 220 kilovolt system. Now we come to the auxiliary system, ACDB. The AC distribution board will take a continuous wattage, and for that, we have to calculate the ampere, and the number of such boards is 1. So continuously, there will be the same 0.09 ampere flowing from the battery to the ACDB. Separately, we have calculated the lighting load when all the emergency lights of the substation glow simultaneously, and that is 570 watts. And that we have calculated separately, which we have not shown here in this table. And for that, the ampere will be this. This is nothing but the load divided by the rated voltage of the DC system. And the emergency lighting system, we have considered 1, so there will be a continuous load. For the 220 volt DCDB, the 220 volt DCDB will also take wattage, and there will be a continuous loading, and the number of such DCDBs is 2. RTCC of the transformer will also take continuous DC load. The battery charger of the substation will also take continuous DC load. Firefighting panels will also take continuous DC load. The SAS panel will also take continuous DC load. This we have to calculate separately. And now we will add. Lastly, let us discuss the table of the 220 kilovolt circuit breaker. It is important that, see, each 220 kilovolt circuit breaker has two trip coils, one closed coil, and one spring charging motor. Because we have considered that the spring charging motor is a DC motor here in our screen. So when the circuit breaker trips, the two tripping coils act simultaneously per breaker, and the wattage of each tripping coil is 225 watts. So the ampere rating will be this. And as we have already told, there are 6 such breakers including the forecasted future. So if we multiply this by 6, we will get 12.24 ampere, which will be taken from the battery by the circuit breaker during bus fault tripping at the first minute of the load cycle. Now, we have already discussed that for the re-establishment of AC power at the end of the load cycle, meaning after 10 hours, we need to close at least one circuit breaker. So we will consider closing one circuit breaker of the 220 kilovolt system, one feeder. And associated spring charging is 9 amperes. Why? Actually, the rated wattage of the motor is 660. And why have we multiplied by 3 here? Because we have considered that at the starting of the motor will take starting current, which is 3 times the rating of the motor. So we will consider here the starting current only, not the running current. So we have considered 3 times the rating of the motor, and that will be 9 amperes. And after that, we have to switch on at least one 220 kilovolt transformer. And for that, again, we have taken that ampere for the closing coil and that ampere for the charging motor. And when bus differential operates, all the feeders trip simultaneously. So this is the tripping current of all feeders. This is the tripping current of all transformers. And this is the tripping coil current of the bus coupler. Now we add all the currents, meaning from 0 to 1 minute. Whatever current comes, we add together, and we will get this current. And from 1 to 599 minutes, we add together all the currents, and we will get this current. And from 599 to 600, we add all the currents, and we will get this current. Now we will come to the load cycle curve, or we will draw the load cycle curve from this. Now, we will draw the load cycle diagram. It means a diagram for the load cycle. First, we will consider 0 to 1 minute, and the vertical axis is the load current in amperes, and the horizontal axis is the time in minutes. Now, from 0 to 1 minute, we will draw the bar with the amplitude of the current of initial momentary tripping of all 220 kilovolt circuit breakers, along with the continuous load. The continuous load overlaps all the time zones from 0 to 600 minutes. After that, we will draw the second block, that is the A2 block, with continuous load only for prolonged hours from 1 minute to 599 minutes. Then, we will draw the third block, that is the A3 block, with the current of continuous load plus momentary closing load. That momentary closing load is the ampere load to re-establish the AC power in the substation, and that will be as per our consideration from the 599th second to the 600th second. The amplitude of that bar will be the calculated total current during that period, which we have shown in our previous slides. Now, consider this portion of the diagram here. The current changes from a higher value to a lower value. That is when we proceed from the A1 bar to the A2 bar. Again, the current will increase from a lower value to a higher value. We have to consider the values of these two current changes. Here it will be negative, and here it will be positive. Why have we done this? Because when we calculate the actual battery sizing from this diagram, we will use these two parameters also. We shall consider here the N cell voltage as 1.85 volts per cell. That means, during the completion of the 10-hour discharge without a charger, the voltage per cell of the battery bank must be above 1.85 volts for each cell. The minimum site temperature we have considered is 27 degrees centigrade. The battery nominal voltage here is 220 volts, and the nominal cell voltage is 2 volts per cell. In our case, the battery is valve-regulated lead-acid, and the battery is of C10 type. That means it will continuously deliver its rated current within the minimum limited voltage for 10 hours. As we have already discussed, A1 is this, A2 is this, A3 is this, and the change of ampere loading from one section to another section is this and that. Now, for the first section, the ampere load is this, the change in load is this, A1 minus 0, because 0 is the loading of the battery before the discharging cycle started. Now we will come to the K-factor table provided by the manufacturer. Here it is mentioned that if the N cell voltage is 1.85 and the battery discharges within 5 minutes, then the K-factor will be 0.8. So we will multiply this change in load with that K-factor, and we will get the ampere-hour capacity of the battery required for this 1 minute duration only. Now we will go to the next section. Here we will consider that the initial block, that is A1 block, will continue and overlap with the next block, that is A2 block. So if the initial current continues for the next block also, then the total duration will be 0 to 599. During that time, the current loading is this, and the change in current is similar to the previous block. Obviously, A1 minus 0. From the K-factor table, we found that if it is 10 hours, then the K-factor will be this one, 11.2. Because 599 minutes is approximately equal to 10 hours. So we multiply this with that ampere loading, and we will get the ampere-hour requirement for the first two blocks if the initial current continues up to the end of the A2 block. Now, what is the change in current from the A1 block to the A2 block? That is nothing but A2 minus A1, and that is here, negative 95.4. This duration is also very near to 10 hours. So the same K-factor will be multiplied with that change in current, and we will get that value, which is negative. So if we consider only that section, section 2, then the sum of these two ampere-hour requirements will give the net ampere-hour requirement, which will be the actual ampere-hour requirement, if we do not consider the last section. Now I will come to the last section. First, we will consider that the initial current will continue till the end. If so, then the requirement of ampere-hour will be nothing but this one. Now the second block is started just after 1 minute. So the total duration is 599 up to the end of the life cycle. The change in current is this. Here also we will multiply with that 11.2 from the table because it is also very near to 10 hours. Or we can take it as approximately 10 hours, and we will get this value, which is again negative. Now I will come to the last block. That is A3 block. The duration of this block is from the 599th minute to the 600th minute. That is 1 minute. During that period, the current is 52.04 amperes. The change in current here will be positive, and that will be A3 minus A2. And that is 21.04 amperes. From the K-factor table, we will get that this is less than 5 minutes. So we will take it as 0.8. And if we multiply that change in current, that is 21.04. With 0.8, we will get that value. Now the total ampere hour in the third case will be the sum of this value, and this value. And that will be 364.03. Now we will multiply that 364.03 with the design margin, aging factor, spare capacity factor, and temperature correction factor. All these factors we have already discussed in the beginning of our lecture. So ultimately, we will multiply all these factors together with the uncorrected cell size, which we have just obtained from our table. We will get the required ampere hour of the battery, which is 573.34 ampere hour, approximately 600 ampere hour. So we will install in our substation a 600 ampere hour VRLA battery bank.
If you found this helpful, don't forget to subscribe, like, and tap the notification bell. Got questions or want us to cover a specific topic? Leave a comment. Thank you.